and we're going to deal with a one-day lesson 2-2. All right. So for the PDF, to begin with, up at the top, again, we have the learning objectives, and you need to read these. Like, does this make sense to me? Because if something looks like it's a foreign language, there's an issue. So does this, what College Board is trying to communicate to you, do you understand how that gets covered in this section? So the first thing is example 2. I'm on page 71, and it's awkward because this says the sandwich theorem revisited. And revisited, we skipped that example yesterday. So how can I revisit something that we skipped? So we'll come back to what this was about yesterday. And I'll back up to page, you can just look up here. I'm going to back up to yesterday's lesson. And all you need to know about the sandwich theorem, that actually College Board refers to it as the squeeze theorem. We're not memorizing theorems or anything, but just that this makes sense to you logically. So this is on page 65 of your book. Again, we didn't do this yesterday, but they're saying we want, you want the limit of this thing. X squared sine of 1 over x. You want the behavior of it as x goes to 0. Oh my God, how could I find that? So they're saying, do you understand, just, you don't have to worry about this, but it's been done. Like, you don't have to, where they get these. This has been bordered by y equals x squared at the top and y equals negative x squared at the bottom. And the blue graph is just bouncing back and forth between the two red graphs. So as you go to 0 from the right, 0 from the left, that's going to take on the same behavior as the red graphs. And y equals x squared, as you go to the left, is going to a height of 0. As you come from the right, has a height of 0. And the same thing for negative x squared. So therefore, the blue graph is going to a height of 0 because it's sandwiched between the two red graphs. So in the same way, we're going to look at this picture in 2-2. For example 2, and this is the graph we dealt with yesterday. This was the graph y equals sine x divided by x. And this is what you have to keep straight between the 2 days. Yesterday we considered what was the limit as x approached 0. And we drew this graph and we turned the axes off, and you saw there was a hole in the graph. And this is an awkward window. Are we good? So you read down here, it's the y's go from -1/2 to 1.5. So this is just a 1 right here. So even though there's a hole in the graph which you can't see because the axes are superimposed above the hole, from the left and the right, as you go to 0, the graph's going to 1. That was yesterday. Today they're saying what's happening is x goes to infinity. So infinity means what happens is this, as you go to the right without bound. What's the behavior of the graph? Negative infinity. To the left without bound. So one way they did this was they said, okay, let's look at the table. So they made x min 100 and delta x 100. And they got these values. And these values are small decimals, and they go to scientific notation. So it appears from the table it's going to 0. All right. Except half the AP test is without a calculator. So how could you do this without graphing it? And that's what this is about. So we say, all right, this is what I've got. Sine x divided by x. That's the question in line 2. But if I back up to line 1, what do I know? I know the sine oscillates between -1 and 1, the sine wave. Yes, we understand that. And the question is sine x divided by x. So if I take the first line and just divide everything by an x, I'll end up with the question in the middle, negative 1 over x on the left, and positive 1 over x on the right. What I want to find is the limit as x goes to infinity of the middle. So I find the limit as x goes to the right without bound of the outside terms. And what is this? This is negative 1 over x. Now, this is a non-calculative part, but if you need to visualize this, negative 1 over x looks like this, which should make sense to you. And as x goes to the right without bound, that's this. And what's happening? The x-axis is a ceiling for this. You don't need to graph it. You could say this. As x gets really, really large, the numerator is staying at negative 1. But the denominator is getting larger and larger and larger. So it's going to a small number over a large number. And the limit of a small over large is 0. It's the limit. See, this thing will never equal 0 because in order for a fraction to be 0, you have to have 0 in the top. But the limit of it is 0. And that's conceptually what you're dealing with limits. It's a little bit of an abstract concept. Negative 1 over x will never equal 0. That graph we just showed you will never touch the x-axis on the right. But it's getting closer and closer and closer, and that's the point. Now, on the right side, we don't need to do this, but you could. It's 1 divided by x. And 1 divided by x is just the black graph. And now the x-axis is a floor as you go to the right. So you just look at this thing and say, the number 1 is a constant. X goes to 100, it goes to 1,000, it goes to 10,000. This value is getting smaller and smaller and smaller so that its limit is 0. So now what? This thing is sandwiched or squeezed between 2 zeros, so the limit of this thing is 0. Okay? Now, what's interesting about this is this will take on the value of 0 because the sign of x is 0. It's your y value. Your y value is 0 at 0 at mod pi, 0 pi, n pi, okay? But even though this thing takes on a value of 0, as you go between 0 and pi, it's going, or 0 and 2 pi, it's going up and below the x-axis, just getting closer and closer, and it's hugging it, okay? So I'll leave it up there. That's your model, and you're going to problem number 9, please. Yeah, what I want you to do, ready? is think about the problem analytically. I know you're tempted to just graph it and then see what's happening on the table. But this is a non-calculator question in May. So the denominator in problem number 9 is behaving like the denominator in example 2. How is the numerator behaving? And one way is think of it like this. Now, I'll draw it. You don't need to draw this, but think about this. If I go to y equals, does it make sense to you that the numerator is 1 subtract cosine x? But I can rewrite that fundamental, or rewrite it by commutative property of addition, negative cosine x plus 1. Which is what? It's the cosine x that's been reflected over the x-axis. So instead of maxing out at 0, it mins out at 0. And the graph's then been moved up 1. Because it's really y take away 1 equals this. So if that's what the numerator looks like, then you go back, here's the picture. Here's what the numerator looks like. And you go back and do that analytically compared to what was on example number 2. Take 2 minutes. So it's going to look like this. So I said, here's the picture I just showed you, which is what? It's the cosine wave It's been moved up 1 after you reflected it over the x-axis. That came first, okay? So the picture of the question looks like this. We're doing the problem without a calculator. So without a calculator, we do the problem analytically. We're saying that 1 take away cosine x, this graph right here, vacillates between 0 and 2. Does that make sense? Because instead of the cosine going from -1 to 1, the graph's been moved up 1. The reflection over here has something to do with the range. So now that's the question, or that's what I understand. Sorry, this is the question. You divide everything through by x squared. If you divide everything through by x squared, then on the left, it's 0 divided by x squared. How is that behaving as x goes to infinity? You have 0 in the numerator, so that's equal to 0. On the right, you don't have 0 in the numerator, you have 2. That's small over large because you have constant and then the numerator is growing. Small over large is going to 0. So here's the difference. The left side equals 0. The right side's going to 0. So the right side has a limit of 0. And this thing is squeezed, sandwiched between 0 and 0. So the limit as you go to the right of the question is 0, which is this picture here. But the issue being that, you know, you have to be able to do this half of the test without a calculator. All right? So we're going to go from here to example number 4. Here's example 4. Now, you got to be very careful to read the subscript. Here it is. X, they want the limit as x goes to 0 from the left of this graph, 1 over x squared. As x goes to 0 from the right. We're not ready. We're not going to infinity here. To right, as you go to the right without bound, it looks like 0 is a floor. Left without bound, 0 is a floor. This is saying what happens as x goes to 0. Well, from the left and the right, it's both. They're both going through the ceiling. So we can drop the superscripts and say the limit as x goes to 0 of the question is infinity. Okay? So that's your model. And you're going to go to 27, except this. Before we don't want you doing this first. You don't graph 27 first. Look at it analytically. How much of 27, that would be a non-calculator question. What do you recognize about the denominator for 27, and how could that help you do the problem? And then after you have it, you can graph it if you want to confirm this. You can, ready? We're talking about you having 2 minutes to do a problem without a calculator in May. If you gave yourself 30 seconds to think about this problem before you started writing, 90 seconds after that would be plenty to finish it. So don't be in a hurry to start writing or start typing your calculator. Think about what you know about the denominator and what that's helping you with in terms of this picture. All right, so we're going to pick up with 27. Ready? So instead of rewriting the question, I factored the denominator. It's the difference of squares. You know that. So what does that mean? That means that 2 would make the denominator 0, and -2 would make the denominator 0. The graph can't have those values. So you're going to have a vertical asymptote at -2 and a vertical asymptote at +2. But without a calculator, how would you know how this is behaving? So I go over here and I pick a number arbitrarily. Ready? Say -4. If I put -4 in here, I would get -4 take away 2 is -6. -4 in here would give me a -2. And the two negatives would multiply to a positive. So to the left of -2, the graph would be positive. If I put +4 in here, same thing. If I put -1 in here, I would get a negative and a positive. And a negative and a positive would multiply to a negative. So the graph would be below the x-axis. So we have two different things here. As the graph, if we look at horizontal asymptotes, horizontal asymptotes is the x-axis. As the graph goes to the left and the right, 0 is a floor. So therefore, we don't need negative infinity, infinity. We can just say, well, we can just combine them to say positive, negative infinity. It goes to 0. Vertical asymptotes are -2 and 2. So as you go to -2 from the left, it's going up. -2 from the right, it's going down. Therefore, the limit as x goes to -2 does not exist. You can't write it in one expression because these two aren't equal. And the same thing's true over there. Okay? That make sense? So we're going to deal with a couple more examples. You're not going to do the problems. I just want to show you a couple things in the textbook. So I'm looking at example number 5. Example 5 says, you have the tangent waves. Here's the tangent graph. Ready? It only has a period of pi. As x goes to a, what's a? Well, a is whenever this thing is 0. So when is the sign 0? When is your y 0? Okay? The numerator is the sign value. So this, they give you the window down here, -2 pi to 2 pi. So there's pi. There's pi over 2. The sine over the cosine. So the sine has a value of pi over 2, but the cosine at pi over 2 is 0, and you can't have 0 in the denominator. So you have these red lines at pi over 2 and add pi, either direction. And what? Every time, as you approach it from the right, all of them, it's going down to the floor. As you approach it from the left, it's going up through the ceiling. But where did it occur? It occurred when the denominator was 0. Now for end behavior, here's example 6. You've got f of x, which is some 4th degree function, and g of x, which is just the first term. The end behavior is the same. Now, this is conceptually a little, you gotta get your mind around this. As x gets really, really large, everything after the leading term brings less and less to the value. The first term in this polynomial will dominate the output. So when x gets really, really large, this has the same behavior as that. And that comes up in example 7. Ready? Here's example 7. Look at A. Find the end behavior model for this thing. All right, first thing is, make sure it's in standard form. Make sure the terms are decreasing. So in A, they are decreasing. So what do? This numerator is going to be dominated by 2x to the 5th. The denominator is going to be dominated by 3x squared. So this thing, without graphing it, it's a non-calculator issue, this will have the same end behavior as this. And what is that? The x is reduced and leave you with 2/3 times x cubed. Now, x cubed is going through the ceiling. 2/3 of that's still going through the ceiling. So we could break this down analytically without drawing the picture that this thing is going through the ceiling. B, on the other hand, what do you notice? The leading terms are the same degree. So this thing is going to a height of 2/5. And you might think about, well, how could I, suppose this is a multiple choice question. How can I look at this thing and possibly figure out if one of the choices is 2/5? That's how. Because everything after the leading term gets discarded. Because the behavior of the function, the height, is dominated by the leading term. So the two leading terms together, their ratio takes you to 2/5. So that's the end behavior of the function. Did I do this? I don't think I did. No, I did. Okay. So that's that for 2, 2.